Hello, everyone. Good morning, good afternoon, and good evening. Welcome to the ITU AI and Machine Learning 5G Challenge. My name is Thomas Pascal from the ITU, and it is my privilege to introduce today's webinar. The AI and Machine Learning 5G Challenge is organized by the ITU, which is United Nations Agency for ICTs. The challenge is kindly sponsored by Xilinx, and we are grateful to Xilinx for the sponsorship they have offered to this year's challenge. The aim of this challenge is to create a community that will solve network-related problems using AI and machine learning. I would also like to take this moment to introduce today's speaker. Of course, the speaker of today is not new. Today's webinar is going to be presented by Michel Polese. He is a principal research scientist at the Institute of the Wireless Internet of Things, Northeastern University. He received his PhD at the Department of Information Engineering of the University of Padova in 2020 under the supervision of Michel Zoz. He was also an adjunct professor and postdoctoral researcher in 2019 as well as 2020 at the University of Padova, as well as a part-time lecturer in fall 2020 and 2021 at Northeastern University. During his PhD, he visited several academic and industrial research institutions, such as New York University, AT&T Labs, and Northeastern University. He also collaborated with several researchers, as well as institutions, including Intel, Interdigital, New York University, AT&T, University of Aalborg, King's College, and NIST. He was awarded with several Best Paper Awards and is the serving TPC co-chair for WNS3 2021 and 2022. He's also an associate technical editor for the IEEE Communications magazine. His research interests are in the analysis and development of protocol and architectures for the future generation of cellular networks, which is 5G and beyond, in particular millimeter wave communication and performance evaluation of complex networks. Now, in today's talk, Michel will introduce DeepBeam. This is a framework for beam management in millimeter wave networks and does not require apparent sequences for the transmitter or any beam sweeping or synchronization for the receiver. This is achieved by inferring on the angle of arrival of the beam, as well as the actual beam being used by the transmitter through waveform-level deep learning. In this way, the receiver can associate signal-to-noise ratio levels to beams without explicit coordination with the transmitter. To demonstrate the generality of the approach, 4 terabytes of experimental data of millimeter waveform was collected. Learning models were implemented on FPGA to evaluate latency performance. So this webinar will also describe how to access this dataset for the waveform as well as the DeepBeam code repository. So I'll take this opportunity to welcome Michel. Good morning, Michel.
Hey, good morning, good afternoon, good evening, everyone.
Thank you so much for joining as well to give us this webinar this year. Thank you so much. The floor is yours.
Happy to be here. All right, so let me share my screen and we should be good to go, right? So can you confirm you can see my screen?
Yes.
All right, great. So welcome everyone to this webinar. The goal for today is to give you an introduction to what DeepBeam is and to show you how you can get the dataset and the code that we use to basically implement the machine learning part for the dataset, hoping that this dataset can be useful also for your research. So this is the outline for today. I'll first describe the motivation for this work, our contributions, then the DeepBeam framework, and a couple of use cases. So where you can, we actually run some numbers to evaluate how DeepBeam works, for example, in the initial access for 3GPP and up. Then I describe the experimental evaluation and how we collect the dataset and go to some conclusions. As Thomas was saying, feel free to post your questions at any time. I will probably get to the questions part at the end, but please feel free to share your questions. So the context in which the DeepBeam work was developed is that of millimeter waves in mobile networks. So as you may know, 3GPP in release 15 and 16 has extended the support of carrier frequency up to 52.6 gigahertz, which is well into the millimeter wave range, with the goal to increase the data rate, the peak data rate and the average data rate available in 5G networks, with the peak data rate moving from 1 to 20 gigabit per second when switching from 4G technologies to 5G technologies. And the reason why the motivation behind this transition to millimeter waves is that at this higher carrier frequency, you have tons of bandwidth that you can use. So if you look at this figure, which is from one of the first papers that actually proposed to introduce millimeter waves in mobile broadband systems, you can see that almost all cellular mobile communications are basically packed into a very narrow portion of bandwidth below 3 or 6 gigahertz, and that there are hundreds of gigahertz of bandwidth that can be exploited when you go up in frequency. So there's very high potential for millimeter waves, but there's no such thing as free lunch. So millimeter waves also come with challenges. So this is a picture that I took at one of the facilities we have at Northeastern that I like to use to explain what are the challenges when it comes to millimeter wave. So the first challenge is the limited coverage. All right, so the signal at higher carrier frequencies propagate at shorter distances. And of course, you can compensate this with directional transmission. So you can focus your energy in narrow beams to basically increase the antenna gain and compensate the decrease in the link budget. However, directional transmissions themselves can be challenging in the sense that whenever you have a transmitter and a receiver that are using directional link, you need to basically make sure that the transmitter and the receiver point toward each other. And finally, another issue is that of blockage. So your body, buildings as shown here in the figure, other kind of obstacles can easily block millimeter wave signals and prevent from having communication with an access point. So all of these challenges need to be addressed to make this system reliable and to make this system actually deliver, to allow the system to deliver on the promises of the bandwidth. So in this talk especially, I will focus on one challenge, which is that of directional transmissions. So as I was mentioning, to basically improve the link budget, the transmitter and the receiver focus their energy in narrow beams. But when doing so, they need to point the beams toward each other. Otherwise, as you can see in this figure at the bottom left of the slide, for example, if the receiver is, for example, sort of listening in a direction where the main lobe does not correspond to the direction where the transmitter is transmitting to, then the gain could disappear, could also worsen with respect, for example, to a scenario with an omnidirectional receiver. So it is critical for the transmitter and the receiver to identify which is the best beam pair at the transmitter and the receiver to be used for communications. And this actually needs to happen in two steps of the connection lifecycle. And the first step is during the cell search. So during when basically the receiver or the mobile user in this case identifies which is the best base station to use for connectivity. And the reason is shown in this figure on the bottom. So in LTE, or in general, when using sub-6 technologies, you can easily go by with omnidirectional signals or very broad sectors, and you can have a very good range with that. However, if you use the same technique, so if you use omnidirectional transmission also at millimeter waves, for example, here at 28 gigahertz, your omnidirectional range will be very limited. And especially if you transition to directional transmissions once the user is connected, only once the user is connected, you will have a mismatch between the range that you can cover with omnidirectional signals and the range you can cover with directional signals. So it is important to use directionality also during the cell search to basically avoid having a mismatch between the control plane and the user plane range. Then the second moment in the connection lifecycle in which you need beam management and you need the user to identify which is the best beam to use with the base station is when the user moves. So there's a need for tracking when the user moves in your deployment scenario and needs to adapt. Both the base station and the user needs to adapt which is the best beam to be used toward a certain base station. And these procedures are challenging and have been the focus of several design choices in the technology standard that use millimeter waves for communication. And traditionally, beam management is done in this way. So the base station has a set of beams, for example, here, beams that go with P1, P2, P3, and P4. The receiver has also a set of beams. And the base station periodically transmits some signals, some synchronization signals in these specific directions. So to do beam management, and interleaves these transmissions with data transmissions. So as you can see, to basically visit all the combinations, so P1 with A, P1 with B, and so on, it takes some time, okay? There's a very high latency and there's overhead introduced by the need for this pilot. So for example, to do an exhaustive beam search with a 24 beam code books at the transmitter and the receiver in 3GPP PNR, it can take up to 164 milliseconds. So, of course, you don't need to do an exhaustive beam search, but this is to give you a sense of the fact that operations which which rely on pilots and on an exchange between the transmitter and the receiver take time and introduce latency. So, when I started basically doing research here at Northeastern, we identified this as one of the areas where deep learning can help. And in particular, we see that deep learning can be helpful in a number of topics when it comes to millimeter waves. So you have your challenges, which are the directionality, the blockage, and the need to support high data rates, which is a potential, but is also a challenge when it comes to do signal processing and, for example, deep learning. So all of these challenges basically introduce complex control procedures, for example, beam management, introduce the need to do coordination among the network nodes, and the need to perform quick reactions. Okay, so we see here a crucial point where AI can play a role to optimize the operation of 5G networks at millimeter waves, for example, with predictive policies or autonomous control policies. And DeepBeam is an example of a framework that actually does the second thing. So it does autonomous control to basically avoid the latency introduced by traditional beam management schemes. So if you remember, this first part of the slide is exactly the traditional beam management schemes with specific pilots for beam management interleaved with data. Okay. So here at the bottom of the slide, I'm going to show you what DeepBeam does. So DeepBeam uses a combination of two neural networks to identify two elements. One is the angle of arrival, so basically the orientation of the receiver with respect to the transmitter. And the second is which beam is being used by the base station to perform a certain data transmission. So basically, DeepBeam can eavesdrop on ongoing data transmissions to listen to classify the beams used in the codebook by the base station, and it can use this classification to basically rank which is the best beam that the base station should use to communicate with the user. And at the same time, it identifies this angle of arrival. So eventually, there's basically an exploitation of ongoing data transmission, so no need for pilots, and there is no need for the exhaustive scan at the receiver. So this has the benefit to reduce the latency and the overhead on your network. And I'll go into more details as of how DeepBeam actually does this. So to summarize the contribution of this work, which has been published at MOBI of 2021, co-authored with Francesco Restuccia and Tommaso Melodia. So this is the first waveform learning framework for mmWaves. It allows to speed up the initial access and tracking. There's no need for pilots. And besides this, we present an experimental validation based on a dataset with 4 terabytes of raw waveform that we collected using multiple radios with different RF chains. So radios from NI and Sibeams, and radios from PyRadio, a small startup in New York, with multiple combination of the transmitter and the receiver and multiple spatial configuration. So the dataset is actually available on this website. So when we get to it, I'll show you how you can basically get the access, get the dataset and download it. So just note this website, which is the one that will give you access to the dataset. So overall, we showed that DeepBeam is capable of achieving a high accuracy. So more than 77% with a 24 beam codebook. And actually, there's space actually to improve even further this accuracy. And that it reduces the latency by up to 7 times with respect to typical configuration for 3GPP PNR initial beams. So let's get into it and let's take a look at actually what DeepBeam learns. So in the first row, you see the first classification operation that DeepBeam does. So basically, each particular beam in a codebook of a base station excites the antenna element of the base station in slightly different ways. This introduces some impairments on the IQ plane that can be classified by a convolutional neural network. Okay? So we've shown that different beams can be classified differently and properly by a convolutional neural network. So the first thing that DeepBeam learns is which beam the transmitter is using. The second thing that DeepBeam learns by, and this I think it's worth mentioning, the receiver of DeepBeam using a single RF chain. So using a single RF chain, so a single set of data, DeepBeam can learn what is the angle of arrival of your signal. So the angle at which the transmit signal impinges on the receiver array. Again, by looking at imperfections and patterns in the IQ plane. And eventually, by using these two information, the beam can adjust the beam at the receiver and let the base station know about what is the best beam that the base station should use to communicate with the receiver. So this is a snapshot of the framework. There's basically IQ samples that are distributed to the mmWave protocol stack and to the 2 inference engines, one for the angle of arrival and one for the beam. And these informations are combined with an estimation of, for example, some channel qualities like the RSRP or the SNR and so on. And this beam information, including the angle of arrival, the transmit beam, and the beam quality metric, is sent back to the protocol stack, which eventually can decide what's the best beam to be used. So I actually see a question on the chat, which is how the angle of arrival is defined for a receiver with a single receive chain. So we define it as the angle between the bore site of the phased array of the receiver and the actual angle at which the transmission is received. And I hope this clarifies in case we can talk more at the end of the talk. So let me give you a little more of intuition behind what DeepBeam learns, especially with respect to the transmit beam. So these are in the top left figure here. You see these are 3 beam patterns for 3 different beams: beam 0, beam 11, and beam 12 of the code book available at the transmitter. As you can see, each beam pattern has a specific shape with a main lobe and some secondary lobe. And also, as you can see, beam 11 and beam 12 are similar. Okay, so they have the energy of the main lobe focused in more or less the same direction. So what the beam does is it looks with a convolutional neural network at the IQ planes and at the patterns, at hidden patterns in the IQ samples for corresponding to each beam. And it is basically capable of identifying which beam is being used and which beam corresponds to certain IQ samples. So just to elaborate a little bit more, here you see the average activation value over on the training dataset over the different filters of the first convolutional layer. And as you can see, there are different filters for a specific subset of filters, which are the ones that actually activate. So different filters activate when you have beam 0 or beam 11 and 12. So this actually shows you that the neural network can effectively discriminate between beam 0 and beam 11 and 12. When it comes to beam 11 and 12, the activation is slightly different, but not that particularly different. And this actually makes sense because beam 11 and 12 are very similar with respect to their beam pattern. Okay, so I hope this gave you an idea of the intuition behind what basically DeepBeam learns. So let's take a look at a specific use case for DeepBeam, which we developed based on the initial access in FreeGPPNR, so the cell search process. And as I was mentioning, in the FreeGPPNR cell search, the base station transmits periodic synchronization signals, so SS blocks, in different directions. With n SS blocks that are grouped in a so-called SS burst, which lasts at most 5 milliseconds. Okay. Then SS bursts, so this group of SS blocks, are repeated with a certain periodicity, TSS. So during an SS burst, SS blocks and data are interleaved. Okay, so it's not just basically bytes. So it is possible to compute how long it takes to perform a full search scan versus a number, basically by dividing the number of directions you have to scan over the number of beams in a certain SS burst, multiplying by the periodicity of this SS burst and adding a factor that can adjust for the duration of the scan in the last SS burst. And I won't get into details here, it's a little complex, so I'll just refer to the paper where we basically explain the meaning of this notation. But what I'd like you to get from here is that the time it takes to perform the initial access is proportional to the number of directions to scan, and the periodicity of the SS burst and the number of blocks that you send in an SS burst are two parameters that you can pick. We also evaluated the initial access latency with DeepBeam. So DeepBeam doesn't rely on pilots, but needs to eavesdrop on ongoing transmissions. So basically, you need to collect Xi samples, okay, to perform a classification. So, for example, you need to collect for this specific convolutional neural network, you need to collect L times K samples. So given that NR is based on OFDM with S subcarriers, you need E symbols, which are the ceiling between the ratio between Xi and the number of subcarriers, assuming there is no oversampling and so on. So we can compute the time to perform the data collection in this way, basically the number of the symbol duration times the number of transmit beams in the transmitter codebook times a factor that accounts for the fact that basically the base station may or may not schedule a beam once or more than once. Okay, so this is basically the time it takes for the data collection. Besides the time it takes for the data collection, we also compute the time to do the processing inside the convolutional neural network. So for the initial access with the basic initial access, the baseline, we do not account for any processing time to put ourselves in the worst possible case for DeepBeam, but we actually computed the processing time for the convolutional neural network in DeepBeam because it's not a simple operation and can take some time. So we exploit pipelining. So basically, we have an end-to-end latency and a latency of the slowest layer of the convolutional neural network. And the formula that you see here on the bottom is basically the overall initial access for latency for DeepBeam. So we actually implemented the CNN on FPGA. And we got some numbers based on it was a naive implementation, so it can definitely be improved. But these are some of the numbers we got for the end-to-end delay and the slowest layer. So when you combine all of these 12 beams at the transmitter and the receiver, 400 megahertz bandwidth, 3GPP neural SG3, you get these comparisons. So here you have different SS block periodicities with the basically the 3GPP NR exhaustive scan latency and the DeepBeam latency according to different values of this value J, which is basically how many symbols are scheduled for a certain transmit beam. And as you can see, in a typical configuration, which is the one with TSS equal 20, DeepBeam can improve by up to 7 times the performance of the 3GPP NR beam sweep latency. So this shows that these kind of approaches can have promising results. And we also elaborated on another use case where basically you have vehicles that are eavesdropping on other vehicle transmissions, and when you basically switch the beam, you want to communicate to other vehicles, you already know which is the direction you want to use, and you don't need to repeat any tracking or initial access phase. So just to make another example. So based on this evaluation, we said, let's evaluate how well DeepBeam actually classifies the beam. So, and something that we did, and I think distinguishes us from most of the papers that are trying to apply deep learning on millimeter wave system, is an experimental evaluation. So when it comes to millimeter waves, I think there are a lot of unknowns related to how the signal is transformed inside the RF chain and so on. So these are generally difficult to accurately model at the IQ sample level on simulation. So we thought it was very important to do this evaluation with actual data, so with data from real experiments, rather than, for example, doing training and testing on a synthetic or simulated dataset. So last year, I got to basically perform a data collection over multiple days with two different sets of radios. So with the side beam phased arrays and the NI backend. So these are analog phased arrays. And with software-defined radios from PyRadio, which is a small startup out of NYU, which use digital beamforming, but that we actually used as basically analog beamformers. And for the side beams, we actually had 4 different side beam frontends. So we basically switched the position of the frontends, and we evaluated 3 different configurations. One, the basic configuration with the 2 arrays straight in front of each other in a room. One, a diagonal configuration with the arrays slightly tilted, still inside the same room. And one with an obstacle in between the transmitter and the receiver in the basic configuration. So this summarizes the different configuration that we for which we collected data. And this basically amounts to a set of 4 terabytes of raw IQ samples. So this dataset is publicly available. So as I mentioned, there's this website, deepbeam.net. So if you go into this website, you can access there's a link to the paper. And the paper is also on archive in case you don't have access to the ACM digital library. There's a link at the dataset. So the dataset is hosted by the Digital Repository Service of the Northeastern Library. And we split the dataset into different files. And basically the content of each file is described into this README file. So if you're interested, the best way to download them is either using this dataset button, which starts a download from the browser, or if you want to download them from your basically from a server, you can just right-click, copy the link, and my recommendation is use wget on the link generated by the dataset button. We also provide the code that we used to basically train and test our network, and it's a framework implemented in Keras. You can find it in a repo, again, linked to the deepbeam.net website. And here there's an explanation of how the data is organized, what the different files mean, and how basically the code is organized to do the different operations that we do on DeepBeam. So I hope this information can be helpful. Please feel free to reach out in case you have any question or you're not sure of basically how to download the dataset or how to use the code. We'll try to get back as soon as possible. So again, the dataset is publicly available, and feel free to download it and play around with it, because we did an initial evaluation, but there's definitely more research and more improvement that can be done when it comes to the design, for example, of the neural network and so on. So let me show you some of the results we got. So and the kind of results I'll show you are basically related to the classification accuracy either of the transmit beam or of the angle of arrival. So this is these are results based on the NI side beam radius in the basic configuration with mixed SNR. So we have low, medium, and high SNR. And we have a 12 beam classification problem and a 24 beam classification problem. So as you can see, the accuracy with both is rather high, and the accuracy increases as expected as you pass more data. So from L equal to 1 to L equal to 5 to the neural network. But if we actually look at the kind of errors that the neural network does, you can see that most of the time the beams that are misclassified are misclassified among neighboring beams. So if you remember from a few slides ago, beam 11 and beam 12 had basically the same beam shape. So the remaining accuracy that we can improve is basically by accounting that close by beams, which are the ones in which the neural network is wrong most of the time, have actually the same beam shape. So if we cluster them together, we could probably get an even higher accuracy. We then evaluated the impact of the input size. Oops. So as expected, the accuracy increases when you increase the input size. But so these are results on the PyRadio dataset, which is a little smaller because we only used a 5-beam basically problem. But as you can see, in that case, even with just 124 active samples, you can get a very high accuracy, well north of 90%. We also evaluated the impact of the SNR. So these results are based on mixed SNR, so basically low values, medium values, and high values. We also evaluated separately the low SNR and the high SNR case. So the high SNR, again, as expected, everything works very well. Things works less well with the low SNR case. But for example, if you first do your receiver adaptation based on the angle of arrival and then do the transmit beam classification, you can get from a situation like this to a situation like this for your classification problem. Then we evaluated the impact of the location, so how the performance changes when using the diagonal configuration, the basic configuration, and so on. And as you can see, the results are quite consistent. And finally, a very important evaluation is doing the training and testing on different devices. So we train on the data collected on one device, we test on another. And as you can see, the results are kind of mixed. So the results tell us that the features learned by the CNN are a mixture of some antenna-based features and antenna-independent features. So the accuracy, of course, decreases, but it does not drop to a random classification accuracy. So it's still 3 times better than the random. But based on the results, we thought, how can we improve this? So we did training and testing on a mixed dataset. And basically, if you train on a mixed dataset with data from multiple radios, multiple locations, and so on, you can increase your accuracy of 124% or almost 200% with respect to the previous case, so the training and testing on the different devices. So this tells us that there are promising ways in which the framework can generalize to different devices, and we're actually working to try and improve the generalization capabilities of the framework. So this brings me to the conclusion, so that we will have some time for the Q&A. So I hope I convinced you that these results show you that deep waveform learning is effective also at millimeter waves. There's plenty of research that has been done at sub-6 gigahertz. This is the first framework that applies learning on the IQ samples on millimeter wave networks. It enables pilotless approaches that improve the overall performance. And it can be seen as a framework. So, for example, if there are several papers that propose smart ways to scan, basically arrange the sequence of the beams that needs to be scanned, this paper can be applied on top of those papers to basically eavesdrop on the same sequence rather than having to wait for the base station to send pilot in that sequence. So we see this, I show you a possible use case based on an exhaustive search, but this framework can be applied also to a more general set of problems. So as I mentioned, as a future work, we are developing some fine-tuning solutions to improve the generalization capabilities. And we are testing scenarios with more angle of arrival values, basically, and the scenarios with different configurations for the directors. Again, the dataset has been published at deepbeam.net, so feel free to download it and use it. And this is the end of the presentation, and feel free to post your question on the, preferably on the Q&A box.
Thanks a lot, Michelle, for the wonderful presentation, and we would like to go to the Q&A session. So I would like to welcome Vishnu. Hi, Vishnu, good evening.
Hi, Thomas, and thanks, Michelle, for that excellent talk as usual. There are several questions with me, several questions which we discussed over the paper, which may be quite interesting as well. But there are several here also. So Udayji is asking, is the transmitter sending one beam at a time? So could you explain that part?
Yeah, so we have an assumption here that is basically the base station is using analog beamforming, so a configuration where a single beam is transmitted at a given time. We believe the framework can be extended also to account, for example, for hybrid beamforming setup, but that of course can be part of some future work.
Thank you. I think there was one interesting question on comparison of latency with pilot-based schemes and your scheme. I remember I had the same question in terms of when I was reading your paper, in terms of inference latency that you explained, as well as with respect to the pilot-based schemes, especially when the number of beams increase. So could you tell us a little bit about such comparison with 3GPP pilot-based schemes and your scheme with respect to the inference latency gains that you get, especially the optimization and gains that you get?
Yeah, so the latency basically has two components, right? One component is the time to either wait for the pilots and collect the pilots for a traditional scheme, or the time that DeepBeam takes to collect the IQ sample it needs for the classification. Okay, so this is the first component. The second component is the actual processing time, so ranking the beams. So we did not have any numbers for traditional approaches or like actual implementation in base station, so we went for the worst case. So assume no processing time for the basically traditional scheme for the baseline. But it was very important to have some characterization of the latency that the neural network basically experiences, because it takes, as I've seen, few hundreds of microseconds to perform the classification. So we factor that in the latency evaluation. And of course, you can, these specific numbers that we got were based on an implementation of the neural network on the Xilinx, on the specific Xilinx FPGA, based on a framework that Francesco Restuccia, one of the co-authors, has developed. So, but even with this specific number, with this kind of non-optimized implementation, we show that DeepBeam can be faster when compared to a fair comparison, so basically an exhaustive beam search. And as I was mentioning at the end of the presentation, there are several papers that try to improve how basically pilot-based scheme can work. So for example, improving the selection of the direction to observe or the direction that the base station can send. But DeepBeam can build on top of these schemes, and the basically, for our seed, the classification capabilities of DeepBeam can be applied on almost any of these schemes to try and improve further and avoid the need, avoid the waiting time due to the base station multiplexing pilot and data. Basically, this is the overall idea. I hope I hope I answered your question. Just let me know if,
Thank
if you
you.
have other questions on this.
Yeah, thank you. Yeah, I think that's true. In fact, it's an interesting observation that you're making, that we don't have numbers from traditional implementations or G-node Bs or E-node Bs for that matter. It would be good to get such numbers. I personally am waiting for open implementations so that we can take some numbers.
To be honest, the processing time would be basically an evaluation of the SRP or RSRQ or one of these matrices, which based on the pilots, which I don't expect to be significant. And I expect it to be significantly lower than the time it takes to processing in a neural network. So it is probably reasonable to assume that if you see this as a limit, the processing time for a traditional scheme is close to 0, while the processing time for a convolutional neural network is close to these hundreds of microseconds, 300 microseconds, 400 microseconds.
Interesting. I also noted your point about combined approaches, because this need not be a competition between the approaches. Maybe, as you mentioned in the presentation, as well as you mentioned just now, that we can have some combined approaches to optimize the traditional implementations as well using DeepBeam. So that's also possible, right? So that's another interesting point. There is a question here. Faramats is asking, how do you compare your work with capacity maximizing ML assisted beamforming techniques? There are there are many papers which I have seen as well on this particular topic, which is maximizing capacity. What are your thoughts on this?
Yeah, so we basically focused on trying on like for example, the specific FreeGPP use case. We focused on improving the initial access part, because that's how the standard work, and that's how the phones and the base station that are being deployed right now work. So we focused on the specific latency issue rather than optimizing the capacity. Then again, the ranking of especially I see that the paper mentioned hybrid precoding. So as I mentioned, we only consider analog beamforming. So in that case, for analog beamforming in general, maximizing the capacity generally means maximizing the ranking the best SINR beam, or the beam that gives you, for example, the highest RSRP. Okay, roughly speaking, because there can be more refined optimizations and so on. But if you have a limited codebook set, then you are basically stuck with a choice among a limited set of beams, and that is at least how the initial access in FreeGPP NR works. So we focused on that, and probably we can think some more to how this compares to schemes where you can actually design the beamforming vector, but this was kind of out of scope with respect to this paper, so it's a little tricky to do an apple-to-apple comparison with this kind of schemes.
Thank you so much. Aliyu is asking the insight into problems that I guess other problems, more problems that deep learning can potentially address. I think I saw several pointers in your paper, Michele. I mean, references to existing work by others. Especially I remember reading about modulation prediction schemes, as well as other problems that you have addressed. And also today also in the last part of your talk, you talked about some of the other problems that can be addressed together with DeepBeam. Could you help Aliyu to understand the most interesting problems which can be addressed using deep learning?
Yeah, so thanks, Vishnu, for actually mentioning this. The paper has a state-of-the-art section which tries to summarize what has been done with respect to experimental approaches to deep learning at millimeter waves. But to answer to the more general question, I see that deep learning can have a role basically for either introducing autonomous control. So if there is a way, as DeepBeam does, to avoid some message exchange in a control procedure, or to better rank beams, or to better rank access points to be used for initial assay and so on. So this can be one option, for example, for more classification related problems. Another option is to basically consider predictive approaches. So try to anticipate, for example, a blockage, try to anticipate some disruption that may happen on the millimeter wave link. These, I think, are the two most interesting problems when it comes to applying deep learning to this kind of methods.
Thank you so much. Actually, George is asking one of the questions which I had in my mind, which when I was reading the paper, as well as you explained the experimental setup just now. So his question is that did you change the environment? Did you change the different setups? Did you change the obstacle? Did you have different transmitter receiver? Could you explain a little bit about the changes, and especially with respect to the generalization aspect, which you touched upon towards the end, right? So you did talk about the generalization aspect. I think this is important to understand whether this kind of experimental result can be used for generalizing, or do you need more measurements for generalizing? What are your thoughts on that?
So let me share again this slide, but summarizes the setup in which the data was collected. So to directly answer Giorgio's question, the setup, the measurements for the NI radios were taken in the same room, but the elements in the room were organized in different ways. So the position of the radios was basically shifted, and we also added an obstacle for one of the measurement sets between the radios. The measurements for the pi radios were done in a different room, but that has the same basically layout. So it's a 6 meter by 3 meter room, because that's what we could do at that point when we were taking measurements. And of course, it would be interesting to, for example, do measurements with more obstacles, or with an environment with more reflectors, even though, as you may know, like at millimeter waves, the actual multiple components are not as rich as you may have at lower frequency environment, especially when you have a line of sight or a partial line of sight environment. So yeah, definitely something that would be interesting is to collect data in more diverse scenarios. But this is, let's say, something that we thought as a first minimum viable product. So different combination of transmitter and receivers, and different configurations inside the same room of the position of the transmitter and the receiver. And this, as I mentioned, has allowed us to test training and testing on different devices, or training with a dataset collected on a mixed set of devices. And we've shown that the results do not drop at random levels, but still there is space for improvement. For example, training on a mixed dataset significantly improves with respect to training and testing on different devices. So there are different strategies that can apply here to improve this, and I hope that people can use the dataset that we collected to try and test these different generalization approaches to improve on our results, basically.
Thank you so much. There is a question about eavesdropping. Yeah, yeah. So that's another interesting aspect of your work. We had some discussion about this even in your previous presentation, as well as when I was reading the paper. So this, what happens if a UE, Vinod is asking what happens if a UE switches to a cell where there is no ongoing transmission and eavesdropping is not possible? Yeah, so yeah, definitely that's a question. But I want to ask also in the experimental setup which you described, whether did you have this eavesdropping, and what is the level of the eavesdropping did you have in your experimental setup?
Basically, what we did in the experimental setup was the transmitter was transmitting different themes in the codebook, and the receiver was simply listening independently on how it was oriented or on what kind of beam the transmitter was using. So this is basically as close as we could get to eavesdropping, and the transmitter was transmitting not only data or not only pilot, was transmitting actually the sequence, the alternative sequence of pilot and data as it will do in an actual system. So to answer to the other question, if the base station is silent, worst case, the base station will still send the directional pilots. So in that case, we would basically go back to the traditional exhaustive, something similar to the traditional exhaustive search.
Thank you so much. There is another really interesting question from Zarina, which I want to ask. I was just thinking of asking. Well, she's asking, can we design algorithms? Yeah, sure. But my question was that are you, as part of your future studies in this area, are you planning to publish some notebooks or something like that to guide this kind of exactly these kind of questions how to design algorithms, maybe some baseline notebooks, etc., or perhaps a challenge next year with ITU.
So do you mean like
yeah.
Jupyter notebooks?
Yeah, sure.
Yeah. So that is not something I was considering. We can try to do that in case. We actually published the code but you can take and run in any machine. We've required the requirements to basically install the dependencies that are needed. So the code is available with examples and scripts to launch the code, and basically a brief description here of what each file does and what do you need to do to basically trigger the file to run the code. So this is the extent to where we went. To be honest, organizing live notebooks based on this is a little tricky because you will need to basically rely on the data and rely on access to the data. And this I never used I did not use extensively Jupyter notebooks, but from my understanding, you still need a source of data. So getting this source of data for the 4 terabytes dataset is a little tricky. So what we did was using basically a setup with a server that had the data locally and running the code on top of this data. And to be honest, this is what I will recommend too. You can probably follow up and we can talk more about this in case.
Thank you so much. Yeah, maybe we can also discuss about some challenge, and maybe next year we can have something based on your data set. Let me quickly look at another question from Udeji. He's asking, beam steering methodology, is angle of arrival a regression or classification problem?
Yeah, we do a classification for the angle of arrival.
Okay. And there is also one last question which we can take from George. He's asking, during the collection of measurements, do you guys consider uniform weights in the receiver array? There is no beamforming.
No, we did not. We used basically a setup where the receiver was pointing to its bore site, as we think can be realistic in a real setup where basically the receiver is choosing a random beam to start the measurement process, and we stick with that for the measurements in DeepBeam. So I hope this answers your question.
Thank you so much. There is maybe one last question. Zarina is asking, can we update the weights when the user is mobile?
Yeah, this is a very good question, and it's part of actually what we are thinking about for some extensions of this work. And there's definitely ways in which you can either generate a data set based on, for example, typical base station that the user may observe when moving in a certain scenario, or for example, doing an update of the weights as you will do, for example, for your GPS, assisted GPS. I don't know if you're familiar, but when you try to get a fix for your GPS on the phone, you have some assisted information that are actually downloaded from the network. So something like this can also be applied for, let's say, configurations for a framework like DeepBeam.
Thank you so much. I think we are slightly over time. So thank you, Michele, for this nice presentation and patiently answering all the questions. For me, it is personally quite interesting and quite satisfying to see your data set. We were looking forward to seeing this about 6 months back, if I remember right, when we were talking that your data set was still under works. So now we have something to work upon. So it's quite satisfying for me. And also, I think from a standards perspective, I think your impact on the standards world is quite interesting for ITU, I think, because it has an impact, right? You are now making it pilotless. So that's quite interesting as well. Now Thomas is here. That means we need to stop. Over to you, Thomas.
Thank you so much, Vishnu, for handling the Q&A, the discussion session. I would like to, at this point in time, to thank you, Michelle, for taking time to be with us again this year. It's quite nice to see the amount of data set that you have, and sharing the code as well as the research work is quite amazing. And we hope that, as pointed out by Vishnu, we hope that next year you'll be a host for one of the problem statements in the challenge, and we'll welcome you for presentation for the webinar anytime. You're welcome. So at this point, I would like also to thank everyone for participating in today's episode in the webinar series brought to you by the ITU Air and Machine Learning 5G Challenge. We have shared information. We have next webinar on 22 October, a few weeks from now. So please register and attend that session. From me and my colleagues at the ITU Air and Machine Learning 5G Challenge, I would like to wish you a good day. Bye-bye.